So what are stochastic processes? So any process can be divided into discrete and continuous. So let's discuss about the discrete process first, and let's assume there's a sequence of random variables, and in case of discrete processes, the observations are equidistant. So let's say this is y1, y2, y3 and so on up to yn, and we have some observations here at each of these specified intervals. So the distribution that we see for yn, irrespective of the distribution for the previous values, is called marginal distribution. Now this process will be called Markov or Markovian. If the conditional distribution of the subsequent process at yn plus 1 given y1 up to yn equals the distribution for yn plus 1 given yn. So I can state it like this. So yn plus 1 given y1 up to yn equals yn plus 1 given yn, which means that a Markov process depends only on the previous value. And if we talk about the continuous aspect of a stochastic process, so instead of these intervals we have a continuous curve of observations, and this kind of continuous process is called Brownian motion, or a geometric Brownian motion. So that's a short explanation of what are stochastic processes. Now let's discuss a property, an important property of the time series processes, which is called stationarity. So what's the stationary process? So we're seeing that in a time series there might be fluctuations, but as long as the behavior remains the same, the stochastic behavior, and by stochastic behavior I mean the moment to moment, time slot to time slot, the way it behaves, like the jump or the decline follows a pattern where it's centered around a mean and has a certain standard deviation or variance, and there are other statistical properties that remain similar. That process can be called a stationary process, also called as stationary stochastic process. So these are the probability models for time series with time invariant behavior. So what do I mean by that? First, let's look at certain types of stationary processes. So the first one is strictly stationary, and this means that all aspects of its behavior are unchanged by shifts in time. So what do we mean by all aspects of the behavior of a time series? So mathematically the various behaviors or characteristics of a distribution are mean and variance and quintiles, skewness, and kurtosis. So as long as all these aspects remain the same, those processes are called strictly stationary. And so if we shift on the time axis, so let's say we have distributions y1 up to yn, and we jump by m time period, so now we have ym to yn plus m observations, and so the distributional characteristics of this set of observations and this set of observations should remain the same for all aspects of the process, the distribution of the process. Then this process would be termed as strictly stationary. But this can be difficult to achieve, and this can be difficult to observe, and so we also have something called as weakly stationary process. And in this we have mean is defined and finite for all t. We have variance, again positive finite constant, and we have covariance of yt and ys defined by a certain function and which takes a parameter as a shift from t to s, and that value is again, that covariance is again constant and is defined, basically not constant but defined by this gamma function, which takes a parameter t and s, the difference between t and s. So we see that the mean and the variance do not change, and the covariance depends only on the lag and the absolute value of the lag. So such processes are called weakly stationary. We are not looking at other aspects and characteristics of the distribution, such as quantiles, skewness, and kurtosis. Weakly stationary can also be termed as covariance stationary, and this function is called autocovariance function, and because it's taking an absolute value as its argument, so gamma of h equals gamma of negative h. And now let's assume weak stationarity, and if we look at the correlation between a value observed at t and one at t plus h, the correlation between these two is called rho of h, where h is the lag, and this function is called autocorrelation function, the function rho. And so we know that gamma of 0 is sigma square, and gamma of h is sigma square times rho of h, and therefore rho of h equals gamma of h divided by sigma square, which is gamma of 0. And as we know, like earlier we had plotted a stock index chart which looked something like this, but for a stationary process the chart would look somewhat like this, and so it can be seen as it's jumping around a mean value, and this phenomenon for due to which we see a random oscillation around some fixed level. The stationary of a stationary series, time series, this phenomenon is called mean reversion, and there are lots of pair trading models that use this phenomenon to look at statistical arbitrage and find out alpha opportunities there. Now that we've discussed about time series and stationarity of a process, we'll explore this particular process called white noise. So white noise and its various types. So the white noise is the simplest example of a stationary process. So if we consider a distribution y1 up to yn, then let's talk about weak white noise. So weak white noise is a process where we have an expectation of yt at mu, the variance is sigma square, and the covariance yt and ys is actually 0 and doesn't depend on any function or any difference or lag between t and s. And if we assume that this if we are not given mu, then it's actually assumed to be 0, and then the weak white noise process is simply defined by gamma 0 equals sigma square and gamma h equals 0, where if h is not equal to 0, and let's take a look at another type of white noise. It's called IID, white noise process. So IIDs. So IID is independent and identically distributed. So there is no dependence among the observations, and their distribution is same. And so IID white noise process is again like a weak white noise is weakly stationary, while IID white noise is strictly stationary. And so this is weakly stationary. If this IID white noise process has a distribution, say normal distribution, then then this process is called Gaussian white noise process. And finally, if these IID, these observations are IID with T random variables, with V degrees of freedom, then this is called a TV white noise process.